Hello and welcome to Protocol Reverse Engineering. I'm netspooky. I'm a hardware vulnerability researcher at a company. Prior to that, I spent several years doing protocol reverse engineering as a full-time job. I also founded the Binary Golf Grand Prix competition, and I'm the co-founder of the Linux virus zine Temp Out. So I wanted to do this talk for a bunch of reasons. I've had these sort of ideas being built out over time, and I've not really seen too many accessible resources for people who want to get into protocol reverse engineering. So there's a lot of resources that are academic. That could be really difficult to access. They might even be paywalled. There's also a lot of paywalled trainings that have to do with sort of analysis, but a lot of them come from a really specialized angle, whether you're doing like defensive research or vulnerability research. And so I kind of wanted to make something that was more general and to provide context to people who want to actually understand how protocols work and how people actually implement them. And I also wanted to share a lot of tips and tricks that I've learned for people who want to reverse engineer protocols, because there's not really that much information that's been consolidated for people besides a couple of good books, which I'll get into. A lot of stuff is spread out over blog posts, and it's hard to get like the context that you need to actually get into this. So that's really my main motivation for doing this. So what are we going to be discussing? We're going to basically go over the fundamental aspects of protocols, which will just lay out how protocols are structured, how people develop them and things. And then we'll also go through a lot of the reverse engineering techniques that you have to do for protocol reverse engineering. And there's a variety of reasons why you would do one versus the other. And so we'll get into all of that. And then lastly, we'll talk about sort of documenting your findings and actually operationalizing them. So protocol RE fundamentals. So the first thing that I always wanted to share with people when I try to explain protocol reverse engineering is that protocols at their core are meant to be understood, right? They're not, you might not seem that way if you see a big mess of binary data, but there is a method to that madness. Protocols define a syntax and they give meaning to arbitrary values the same way a language does. But just like a language with, verb order, subject, object, verb order, stuff like that, they follow patterns that are common to other protocols. And if they don't have something, they might have something else. They're all these components are little building blocks, and they can be used to understand stuff that is not fully understood or isn't understood at all. So an example of how people do this kind of stuff in the real world, just from a language perspective, is an example here is the Mayan writing system. So this language was actually destroyed by missionaries in the 16th and 17th centuries. They actually burned all of the books that had anything to do with the Mayan writing system. And this was really bad because there was a lot of, obviously, culture destroyed, but the understanding of this language itself and the people who spoke it was difficult to actually ascertain until way later, due to just a lot of different factors. If you watch that video that's linked on the slide, it's a really awesome thing about how this is actually recovered. But they use the properties of what makes up a language to cross-reference between other languages that were spoken in the area. And they're actually able to decipher the script using very small surviving scraps of information. And that's similar to what a lot of people do when they do protocol reverse engineering, depending on what levels they're trying to get at. But you can sort of use other protocols or languages as a guide to help you to actually understand it. And so there's a lot of things that are some misconceptions that I think people have for this kind of stuff, is that there's all these sort of complicated inner workings, and the mental model about it might be really maybe more complicated than it actually is. But at the end of the day, electronic messages that we send are just little pulses of energy, right? It's just like flipping a light switch on or clicking a mouse really, really fast. It's just sending data of some sort really fast. And so we've gotten a lot better at sending pulses of energy really quickly. We started out here with a Morse code operator who would tap out the individual pulses, and then the same sort of job of sending out pulses of electricity are also present here with this Ethernet frame in an oscilloscope. It's the same exact thing. If that lady had really quickly pressed the Morse code operator, they could have tapped out potentially some frames of Ethernet for us here. But Protocols ultimately are a set of agreements, right? Like to actually communicate data over a channel, you have to agree on a lot of really core things. So the basic level of protocols would be things like the logic levels. So like what counts as a one, what counts as a zero, what are the thresholds of whether something is a one or a zero versus being off. There's other stuff like how timing would work with the protocol. So it's how often the data is sent back and forth. The framing is also really important. It's the same as like punctuation, right? It's like how to tell when one message begins or ends. Then the last two are the syntax and the semantics, which is like the structure and the meaning of it. But these all are core to what a protocol is, and depending on what level you're working at, you might have to consider these agreements that we've had to work out to actually make a protocol. And so, as more devices have been developed and want to talk to each other, a lot of these low-level agreements had to be standardized. Some of them were really basic, but they had to start somewhere, like 8-bit bytes. An example here is this AT&T engineer working on this one ESS switch. Back in the day when people wanted to actually communicate with each other, they wanted to use the already pre-existing data interchange infrastructure that existed, because laying down all those lines and having to make your own switches and everything would be a lot of more work than just simply using what's already existing. And so a lot of protocol components actually became de facto standards because of this, because people all wanted to just get in right at the beginning and use something that just worked, and those became just the standards of what people used. So this happens with entire protocols. It's a concept called protocol ossification, which is just when protocols really can't be changed because of how much other people rely on them. And so another core fact here is that people typically don't reinvent the wheel when they're making a protocol. So they'll use common things, as many common data structures and design paradigms and pre-existing things as they can, typically just because it's a lot easier. So once you learn a lot of the basic building blocks that people do use, you can use them as a guide to understand protocols, even if you have no idea where they're coming from. And this is an example here with this the OSI model here. It's still out there. It does exist. There are protocols that use the entire OSI model stack. Yeah, I can get into some of that later. Protocol constraints a lot of the times can be explained by the context that they're used in. You might think that certain things are arbitrary or just kind of done willy-nilly, but a lot of things are done because they need to be done to account for the requirements of a lot of the lower level things that they're using. So they might have to avoid certain values, or they might have to exclude certain things because they need to be fast or they need to be human readable. And so there's a lot of different examples of this kind of thing, and we'll kind of go through them. But in this case here, you can see this is from a write-up that I did called Broadcast Brujeria, which was about putting protocols and tunneling them over existing protocols and how to design for some of the constraints in there. So this was a protocol that the data body fit inside of an Ethernet header, and it had to be done like that because of a lot of the different characteristics of how Ethernet works. And so it brings us to the next point here about how protocols are really a product of their era, right? So we look back into them. There's a lot of protocols that are incredibly old. So there's different constraints that are relevant at different times. A lot of the early stuff that we did with computers would be character oriented. It goes back to the days of teletypes and things like that, where people were typing with typewriters that were rigged up to be attached to a computer, and things being character oriented meant that a lot of stuff was reliant on the characteristics of ASCII, which also had to be standardized. And those kinds of things are what led to some of the kind of ancient feeling protocols of today, right? Like FTP has a binary and ASCII mode selectors, things like that. Email, SMTP still can't use certain characters. There's things like that that kind of are just inherent to the state of how protocols are. And a lot of people, their mindset is going to be, if it ain't broke, don't fix it. Just keep building off of it. It does lead to a lot of limitations, but it kind of helps you to contextualize where we're at. And also, big, huge thing is that protocols can outlive their authors here. So we see here, this is somebody asking for a support for Enron Modbus, which is a type of Modbus, an industrial protocol that uses 32-bit mode for data transfers instead of 16 or 16-bit, which meant that it had to be using a specific library or specific drivers to actually talk this protocol. And it was made by Enron for whatever reason. They don't exist anymore, but people still have to support these because the devices that created them still existed. And then having to interoperate with those older things led to stuff like modern smart meters is what they mention here as still using them. So these things can just live on and become part of the ecosystem that we exist in. With all that being said, we have to keep in mind a lot of these core facts about why, the how and the why of protocols. But when you're starting to reverse engineer, you kind of have to think about those things in that context and what you have access to reverse engineer. So big question that I always ask myself is like, what am I actually trying to do here? You ask yourself why you're reverse engineering. There's a bunch of reasons. You could be doing it for compatibility, right? Like the example with Enron was trying to be compatible with this Python library that would be able to access and talk to smart meters using an ancient fork of Modbus. You can also do stuff like detection engineering and network monitoring. Reverse engineering for those contexts typically is going to rely on you having to do a lot of really actually understanding the nuances of both the protocol as well as the implementations that you're using, just because there could be, malware or other things that are abusing these channels in a way that would be invisible to normal tooling. If you look at the write-up that I did about tunneling protocols, that's also an example there too. But doing that requires you to actually have a good amount of understanding of what the protocol actually does. Malware research is another big thing. If you are looking at pieces of malware that talk back to a C2 server, they will often have some sort of side channel or something that they can use for communication to command them. They might do data reporting back and have to encrypt it. And having to understand all of the network functionality that a piece of malware does is very important. So there's often custom protocols and file formats that are used, which are really useful to RE. Same with vulnerability research. There's a lot that you can do with a protocol over the network. A lot of things happen. There's a lot of RCEs that could happen over the network. Understanding the nuances of both the protocol and the implementation are super useful for vuln research. Another thing is a protocol may be lost, right? Protocols actually can get lost because the vendor doesn't exist anymore. Also, if the actual library itself was, say, paywalled or distributed through some specific channel, if that channel doesn't exist anymore, but you're still supporting it, there's really no way for you to get the protocol library. So there's actually a lot of examples of this, and I've actually helped vendors to recover lost protocols from some of these sorts of artifacts here. Another big thing also related to being lost is server check and DRM bypass, because if the infrastructure that exists to support some device needs to talk back to some server using some specific protocol, you might have to reverse engineer the device to even use it anymore, which is very common across a lot of things actually. And it's super important for us to be able to have things continuing to work by having some of these skill sets here. Another big thing too is you might just want to build your own implementation, right? Like you could do it for fun, you could do it for a business or open source or whatever, but you would have to reverse engineer to do that. And then the last one is, of course, the one for the hackers here, which is curiosity, because things are just kind of weird sometimes and you want to figure out what's going on. So what kinds of protocols do people RE? So you might be wondering this. These are kind of the main ones that I've tended to RE. There could be more depending on your use cases, but typically it's extensions of something known, right? If there's like a known protocol that people use, but there's some goofy implementation of it somewhere, you might want to know what that is doing. There's a lot of undocumented or poorly documented protocols that are out there that you also want to take a look at. Same with proprietary protocols that are either have a vendor SDK that is under lock and key, or it just isn't documented and they don't want you to find out about it. It's another big thing. And then specific implementations are also interesting too, because a TCP stack isn't going to be the same from Linux to Windows to an RTOS to something else. So you might want to understand what a specific library and even a version of a specific library or stack actually is doing. And so, oops, did I just skip fast? All right. So now we're going to get into the protocol RE techniques here. And so there's four major ones that I tend to classify a lot of things as. And so we'll kind of look into what these all mean. And so it's actually super important to do your due diligence and try to figure out how many of these you might need to do and what is available in each of these domains that could help you. Also super important to mention is just trying to remove sort of like your preconceived notions about how a protocol is supposed to work from the beginning, because as you can see, and I'll demonstrate, there are a lot of cases where what you might think is happening is actually not the case. So the first one we're going to start off with here is packet analysis. So it's often a really good way to understand a protocol, and it can be done in a bunch of different ways. There's live capture, and then you can also just look at packet capture files. You can also sometimes debug stuff within a binary itself, which we'll get to as well, that is, you can see the full contents of a packet from a debugger, which is really fun. Many of these techniques, though, can really be done on any form of binary communication and even file formats. So it's not limited to simply just network packets. It can be a lot of different things. There's some actual file formats that are just serialized protocol data. An example is MIDI. If you ever looked at a MIDI file or a MIDI system extension file, it's just protocol messages in there. So before we go any further with PCAPs, I wanted to bring up this spooky fact here. So a lot of people will say PCAPs or didn't happen. It's you can see this cross stitch here, beautiful cross stitch that says PCAPs or didn't happen. I do have a lot of problems with this statement because PCAPs really are limited, and they're limited by your device's ability to capture packets and to also record them at the same rate and order that they appear on the wire. I've actually seen out of order PCAPs based on devices that talk too fast for the network interface to actually process it in time. There's also limitations that are based on your software parsing ability, right? Like if you have a Wireshark or TCP dump, there's still things like dissector and parser bugs, and they can, even if you are capturing, you can still be limited. Things could be truncated. There's a ton of different things that can go wrong. So my thing is PCAPs or you didn't capture it. I guess I don't know. It's kind of a weird saying, but just make sure that you trust but verify. So getting into this too, PCAPs really are just a snapshot, right? The limitation of a single PCAP is that it can only really tell you what happened, what it saw. So it can't show us what happened before or after. And if you use something like a filter, that can remove important details of the network flow. And I've actually had this happen to me before where somebody had given me a PCAP and I was reverse engineering the protocol, but there was multiple ports that were used for the protocol. And so I kept seeing one side of a conversation. I had my inferences about what it was doing, but then I asked if there was what the filter was, and it was apparently filtering on only one port. So I wasn't sure if this was some isolated thing and they gave me everything that they knew about the protocol or if it was the full network trace. And so I ended up having them give me a full PCAP with a bit shorter of a capture time, but it gave me all of the packets that I needed to RE the protocol. And some protocols it's very common to use, or not very common, but it's common in older protocols to use 2 or more ports for sending and receiving data. An example here is FTP, because FTP was actually designed for NCP, which is a communication protocol that was before TCP/IP. And so that had only had single direction data channels when you connect it to something. So you had to have a send and a receive channel for this, which is also common in serial protocols. But that's the example of why FTP does that. Actually, come to think of it, the device that I was discussing with multiple ports was also an industrial device, which was part of a bus. So the bus protocol was based on another serial protocol, and it kind of all follows the same trajectory. So messages can be truncated as well. You have here the Shrek with the snaplen. You can set a snaplen, which is how much of the packet you actually want to capture. If you don't know these kind of things about your capturing tools, you might miss out on data, which I've seen many times. So just an example here, this is what the PCAP format actually looks like. So there's 2 major versions. There's the PCAP, which is just a buffer of messages that can go into the file. But the pcap-ng file actually has a bunch of metadata blocks, and it's separated into blocks, which you can use to put other information about the capture or protocols or whatever you want. Just both good to know about. They're fairly simple protocols, are very simple file formats, but it's good to know if you want to figure out if something is actually a PCAP. Also, when in doubt, do a hex dump on the PCAP, because Wireshark will try to load anything, and so it will just mess it up if it doesn't know, if it thinks it's a PCAP and it actually isn't, or nothing was captured. And so here's, I guess we can get into getting packet captures here. So there's a lot of places where you can get them. You don't have to always capture them yourself. Sometimes you can find them uploaded to forums or public analysis sites. There's also data sets that people will put on GitHub, which I really like too. Sometimes they can fall off a truck and you just pick it up and it's where it comes from. But if you have the software or the hardware that implements this protocol, then you definitely should try to make your own PCAPs as much as you can, even if you do have access to PCAPs, just so you can compare them, because you're going to have a whole different context in which it's used. And so Wireshark or TCP dump are the two standard tools that people kind of use for making packet captures, but a lot of hardware devices will also support PCAPs and can even capture them for you from the hardware itself. And raw data as well as incomplete data is going to be better than no data. So if you can't fully capture a thing, still getting the hex dumps and things like that is still going to be a lot better than doing no packet capture at all. So how do you actually do your own? As I said before, with Wireshark, TCP dump, T-Shark is kind of the main ones that you will use for your interface for it. But you can use things like LAN taps to tap Ethernet cables. You can capture Wi-Fi and raw Wi-Fi frames from your Wi-Fi card. BLE capture is pretty cool because there's a lot of devices that will do BLE PCAP capture. But if you do something like HCI Snoop Log on Android, you can get a PCAP of BLE traffic for you to analyze yourself. Another thing people don't typically know about is you can capture USB traffic as well. So if you have a thing that's going over a USB interface, you can actually capture, with bulk transfers or whatever they use to transfer data. You can get those and then pull data out of those. There's also a lot of radio capture software that can generate some, and you can definitely fake PCAPs by putting data over a specific channel. By sending raw frames, or you can even generate PCAPs yourself by following that PCAP format, or write your own raw PCAPs. And you can use tools to edit PCAPs as well. And my advice is to try and collect as many packets as you can. Another thing I want to say real quick before we get going here is if you don't have a lot of gear, you can root an old router to capture packets on them, or you can at least try to. Definitely check exploitdb about any routers that you might have lying around that you have permission to take over. That might be a way for you if you need to analyze a whole LAN. So let's take a look at the analysis first steps here. So the thing to keep in mind when you're looking at a PCAP is also that you are examining what they call the wire image, which is just what is transferred over the wire between two devices. It might not be the full protocol. It could be encrypted or encoded or compressed or whatever. Just keep that in mind when you are looking at a PCAP. So when you start off, you want to know what all the known traffic is. You want to see what protocols you're familiar with and see what devices are speaking those. And then after that, you want to look at any unknown messages. So anything that wasn't parsed by Wireshark, anything that looks kind of weird. There may be big blocks of messages being sent back and forth, or misparsings, and Wireshark might complain. Look for those kind of things. Within those, you want to identify what the encapsulation and transport mechanisms are used, right? Like, is it going over TCP or UDP, or is it some sort of other Ethernet protocol? Just the questions to ask to yourself to be able to build a model of what the communication is. After you do that, you want to start to isolate the unknown traffic from the known traffic and anything that's interesting to you. You can use like ports or addresses or any other identifiers that can be used to filter out the unknown protocols from the known stuff. And after you do that, you can then start grouping things together and characterizing any unknown traffic. So spooky fact number 2, everything is made up and the ports don't matter. So this is something that I've just wanted to explain for people out in the open here. Port numbers are just a pointer to where to send data. There's assigned port numbers, there's well-known ports, but nothing stops a protocol from running over whatever port it wants to. The OS might even have things running on certain ports, but you can always, kill those processes if you need to. And also, another huge thing, you absolutely do not have to memorize every port number in every protocol. People have asked me this before, and it's just not something that you need to do. Your computer also has a list of them somewhere, usually. So if somebody says on some test that you can't use Google, you can use your computer still. Your computer has that information on it. Look up where it is on your OS. There's a list of well-known protocols and ports. And so different OSs also consider different sets of ports to be ephemeral, and they might treat certain things differently. Everything is implementation details, so just keep that in mind. You don't have nothing here is going to really be set in stone, even though there are things that are built off of foundational stuff. There's still a lot of abstraction that we deal with, and we have to keep that in mind. So here's my basic rundown on how to characterize unknown traffic. So these are kind of the main ones that I typically use to start off with as my baseline. So I started off with stuff like frequency analysis, which is how often are messages sent. I use in Wireshark, there's a column that you can enable for the time. That's the time delta. And so you see how fast messages were sent from one after another, which is super useful if you're looking at a lot of data that's all kind of the same ports and protocols, just to see, how fast this protocol even is. I've seen PCAPs that are 2 seconds long that have thousands of packets in them, and there's so much happening in, the blink of an eye. So really useful to keep that in your head. How often are the same messages sent is another big thing too, because things like beacons, things like sending different requests for initiating contact, those are all things that you might see just happening really quickly at a very consistent time. You can characterize messages like that by if they're being sent at a certain rate, maybe every second, every 5 seconds, whatever. Those are all characteristics that you want to keep track of. Another thing is, do you know what values are common inside of a packet, right? There's going to be values that may be repeated, magic values, things like that. You just keep an eye out for them if you see them inside of your packet. And the next thing after that is I do differential analysis. So this is how often do the packets actually differ, right? Because if there's the same message being sent over, you might have 1,000 messages, but there's only one that is different. So you got to figure out where those are. When you find if packets do differ, you figure out where in the offset of the data do they actually differ, and how, because there might be just a couple of values that are being different between the two of them. It could just be a single byte that changes, or it could be a number being incremented. Those are all things you want to know. And the other thing here is the timing analysis, which is also part of frequency analysis too, but you want to know how often each individual node on the network is sending a packet. Who sends it, how often do they send packets, and what's the time delta between them. There's certain things that are, as I said, beacons, but there's other stuff where there's just things being published by a certain node, and that might be your most important node on the network. Another big thing is the length as well, which is like how long are the packets, right? Does the length correlate with the message content? Oftentimes it does, and if you can sort by the length of each individual packet of what you're looking at in Wireshark, then you'll be able to see if there is a correlation between those. So the thing that I like to try to do is to sketch out what an average packet looks like and see if I can identify any data structures or message types. So in here, it's actually a tool that I'll discuss in a second, PDIF2, with a packet average with a heat map with frequencies or how often a certain value appears within a packet. Another thing here is the isochronous real-time Profinet, which is an example of time slicing. There's certain traffic that will only appear in 1/4 of a period of time, like a duty cycle of like 25%, that is one type of traffic, while another traffic is another type. So these are kind of things that if you were looking at certain protocols, you might see attributes like this, which are just something that you can inform yourself on based on things like timing analysis. So let's get a little bit into the common components of protocols. So There's things that I will see in protocol headers that are fairly common. Things like magic values, which will be right at the start of a packet. They could also indicate the start of a section of a packet. An example actually is the DHCP, which I just showed. The DHCP cookie is actually at the end of, or it's in the middle of the packet towards the end where all the actual options are. That's an example of a magic value that appears later on in the packet. There's also sequence numbers, which you'll see incrementing over time. If you ever see a value incrementing, in a very uniform way, it's most likely a sequence number. This is different also from transaction IDs, which are things that are repeated by the sender and the receiver as a kind of a data integrity thing to say, oh, here's message number 7, here's a response number 7. There's also things like node IDs and addresses. So these are values that can be associated with a specific sender. Same way an IP address is, there could be routing and things inside of the protocol that have a node ID that is unique to a specific device. The length fields are also really common inside of a header, which will just tell you the length of the message contained. And so if you look at a packet's length in hex, you can look to see if any values look similar to that value. And then there's also command and message types, which will usually be at a very specific location and related to the overall packet content. So if you see certain things that are changing slightly or changing early on in the packet, if you see certain numbers that appear to be correlated with like the length or the data that's inside of the packet, that might be a command or a message type field, which can just differentiate between how it's supposed to be processed. So other protocol components that are really common, so there's byte order, is something to just know about. So protocols will usually be in big endian network order, that's what they call it, but the data inside of the packet might be little endian. So there might be things that you are confusing because things that are little endian, like application style things, might be easier to process if they're stored a little endian, but everything else within a packet and a lot of things that are protocols are designed are using big endian stuff, so they might actually need to be in mixed endian format. Another thing to identify is timestamps. There's a write-up that I did about how to identify certain ones. You really got to know when a packet was captured to be able to point them out usually, but I typically will get the hex value of our current timestamp and will just try to look for values similar to those values inside the packet data to see if that was being sent. Another thing is bit fields and flags, right? So if you see things that are even numbers like this, like 1, 2, 4, 8, any of the other even hex values too, those could indicate a bit field because it could be one bit that is set within a byte. I try to look for consistent, even looking numbers just to see those. You can also look for IP addresses and MAC addresses, which are metadata that you could already correlate within the other packet. So if there's the MAC addresses being sent, and it's the same MAC address as also in the Ethernet source or whatever, or Ethernet destination, those can be things that you can use to say, this is what this data is, and this is what this field size would be, and then build off of that. Another thing is checksums, which often appear very close to the data, but they're checksumming. And so if you see a packet that changes just slightly, and it might change slightly in one spot and in another, depending on how the arrangement is, one of those things could be a checksum if it changes in increments very little and there's a very small change at another field. Just try to keep that in mind. There's CRC calculators which you can use also to if you suspect of a data area being privy to some checksum, you can use those as well. That's in the resources page that I've provided here. Padding and data alignment is something that you can suss out by looking at these other protocol components, because if you see, things are going to be based on compilers and how those compilers represent data. And so there's going to be some sort of alignment usually within a packet of the data sizes that they're using, but you can also see padding too. If there's padding that has to pad up to a certain size or whatever, those are things you can also look for that can help you suss out the structure of a packet. I also usually look for zeros and FFs just to see what a data field might be. Just very easy delimiters to look for. And the last one here is just auth data, which could be a login or a token or password or whatever, and it's usually related to like a node. So if you see a node sending a certain auth data or something that looks like auth data, if everything is sending the same thing, it might not be auth data, or it could be a generic password or something, but you typically can correlate those between different sessions and nodes. Big thing that I also look for when I'm starting out something beyond trying to suss out all these other things is looking for strings. So if you see those repeated values, if you see things that look human readable and they actually are human readable and not just things that happen to be printable characters, you can use those as an indicator of how the data is structured. There's only a few common string representations that you see. There's going to be stuff like length first, which will just store the length of the string prior to it. So if you see a printable string and you see it's five characters long, and then you see a 0.5 right in front of it, it could be a length first string. There's also null terminated strings, like in an array. So if you see strings and they're separated by zeros, that's also an array of strings. And they can also be in UTF-16, UTF-8, any other sort of way of doing those encodings. But the last one is fixed width strings, which should just be strings of a certain size. These ones that are in the example here are 16 bytes wide, so these are going to fill up and they're going to take up the same amount of space regardless. So you can use strings often to help with RE and OSINT tasks because you can just Google those strings and find and see if anybody else has discussed them somewhere. I also usually keep a big list of the strings that I find that do seem interesting, even if I haven't found them online, just because they might show up in software somewhere. So another common protocol component to discuss here too is the TLV, which is the tag, or depending on where you're looking, type, length, and value. It's just a data structure. It's just something that there's a tag that represents what type of data it's going to be, or how you're categorizing this type of data, and then the length of the value, and then the value itself. They can also be nested. You can have tag, length, and then right after that tag and length is another tag, length, and value. It can go on super far. An example here is this TLS client hello.xx file, which just shows how nested all of the different options are for TLS. And that's very common. You'll see TLVs all over the place. So here's some helpful enumeration tools. So for this talk, actually, I put out pdiff2, which is a newer version that I'm working on of pdiff, which was a packet diffing program that I had written a few years ago. It can help with basic enumeration tasks, and it works with both PCAPs and text files. The link to it is inside of the resources page. There's also pdiff wasm, which Remy, our pal Remy Matata, had written as a WASM in-browser version of the original pdiff tool, and it's really cool. I like Network Miner as well to enumerate, just because it can pull files out of a PCAP and reconstruct them based on certain session metadata. There's also ngrep, which can be used to do regexes across PCAPs, and then also binwalk is really cool because you can find file signatures as well. And Wireshark has a lot of traffic analysis tools built into it, so definitely explore those and spend a bit of time with the analysis tab of Wireshark, because there's a lot of stuff that is really helpful. It's very useful to have a diverse tool set too, because you shouldn't rely on just one tool's output, because there could be so many issues with how one tool parses something versus another. So diversifying your tool set is very, very helpful if you're doing protocol RE. Protocol features to know. I have two more that I want to just discuss real quick. So there is fragmentation and pipelining. So single messages of a protocol can be split up into fragments. This is another relic of the agreements that we have to make. There's things like the MTU, which is the maximum size of a packet that can be sent over a network. Things have to account for stuff like that, especially for streaming and sending file data. So typically things are split up into fragments, and they can then be reassembled, and there's other data about how things are reassembled. If you take a look here at this IPv6 fragmentation diagram, this just goes to show how this actually, the data gets split up and given its own header and then sent out. Multiple distinct protocol messages too can also be sent in one packet. This is called pipelining. It's common in a lot of different protocols, and it can be used for sending multiple things before their act, essentially. And then on top of that, multiple pipeline messages can then be fragmented across multiple packets too. I've seen this in a few protocols where it gets really complicated to parse, because you have to know what the first message was to be able to decode all of them. Otherwise, you're picking up somewhere in between some data stream. It can be really complicated though, which is where things like HTTP request smuggling come into play, which is an example of pipelining, where you can send a post request with a certain length and then also have a GET request inside of it that's also valid, and the server just thinks, oh, I got 2 requests, and then sends you back data for both. Pretty fun kind of bug. The other thing here is just encryption. Just as I said before, you're looking at the wire image here, but there could be things that are just simply encrypted, and a lot of protocols use these. If you look for areas containing high entropy data, that's a big thing. Data that is a lot of distinct values versus just a few values. You might see a lot of zeros normally in a protocol, or a lot of text, but in other ones you see just a lot of diverse bytes. If you do suspect something is encrypted, you can examine the traffic for a key negotiation, which can happen between 2 different nodes. If they send a couple of short messages followed by a bunch of long encrypted looking messages, that's a good indicator. A lot of stuff will use stuff like TLS, but things will roll their own sometimes too, so you kind of have to confirm that with software RE usually. There's also compressed and encoded data which may look encrypted, but that you have to confirm whatever you can with software RE. You shouldn't try to break the encryption from the wire image itself. It's not usually the best use of your time. Okay, so now we'll get into software RE here. So the thing that I try to do the most with doing software RE is to just think like a developer and try to put myself into their shoes, get into their headspace, and think, what were they actually trying to achieve with this protocol? What were they trying to do? Because there's certain things where it might be for a high security, safety critical environment, or this protocol, whatever they were designing it for is meant as a generic sort of wrapper for things. There's a lot of reasons why somebody would have designed a protocol. So you think about all of the things we've discussed already and brainstorm from there. And if you're looking for bugs too, think about what kind of aspects of a protocol would be difficult to handle, or things that you've seen about this protocol specifically that would be difficult. Where would you mess it up? Where would be the challenges? And then also think about any constraints they might have had, or any considerations they might have had to make that are extra beyond what a normal protocol we need to have for a normal protocol. So the very first thing that I do is to do OSINT for software RE, to ask myself, are there any open source implementations of this that I can read the comments of, or if there's any leaked source or anything like that, the source has been shared in some way. There's also, does the vendor document any aspects of the API? Sometimes the vendors will use a software library, and the software library is just wrappers to a thing that gets linked into your thing when it's at compile time. Sometimes there's varying levels of how much information they actually give you about the protocol. So looking around and just seeing if there are anything that you can look at is really helpful. But then also big thing, has anybody else reverse engineered this software? Because there might be somebody who has even done a part of it, right? They might have documented just a little bit about what they saw, and it might not be a full RE, but if somebody was able to give you even a little bit of information about it, it can go a really long way, especially if you can talk to that person too. Thanks, motorcycle. Okay, so the other thing is there anywhere that users of this software chat, users or developers or anything? You want to know if there's any place where people are going to be discussing it, possibly sharing information about it. Stack traces. I love seeing stack traces when somebody posts them, or a screenshot of the UI or whatever. Very useful bits of knowledge. Also, search for the strings that you may have found in the packet analysis phase and other protocol characteristics like the port number or whatever, or even known multicast addresses and things like that. Look for those things and see if there's any references that are relevant to you. So, thing to go over about software RE, a lot of the stuff that we're going to be discussing is going to be pretty standard software RE type of things, but the kind of network specific stuff is what we're really trying to focus on here. The network communication APIs that are used are typically really well defined, because if they want people to develop on it and use it, they're going to have to define how to use these APIs and how to actually initiate, close, and manage connections in a nice way. And so a lot of operating systems will use well-defined stacks and well-defined flows for their network communication and their drivers. And they'll typically try to abstract things as much as possible because ultimately we have a physical connection to a device, right? So all those things like the logic levels and the framing and all that, you don't normally want to handle that in software as a regular user. So they try to do stuff like having a physical connection that is either like a file descriptor or a handle or some sort of pointer that you can send data to and manipulate. RTOS is going to be doing the same thing. Usually any other kind of firmware is going to have some sort of API that is standard that they can be using for this kind of communication. And it may wrap other existing libraries. There may be a bunch of other, indirection to the actual functions you're using, but they're all going to ultimately be pretty similar in how they operate from a user perspective or programmer perspective. And so for non-network protocols like USB, there could be other platform-specific things, and there might be stuff that's part of your platform that you don't even know about. Like there is a MIDI subsystem for Windows. Like you don't even think about those kind of things sometimes. But they're all going to be there for you to actually use if you need to. Because at the end of the day, it's all just I/O, right? Like software does the same thing whether you're doing network stuff or disk I/O or whatever else. It's going to be very similar. And here's an example here on the side of a UDP packet going through a piece of firmware through all the driver layers. And so really, really common one just to know about if you're doing any kind of protocol RE or Berkeley sockets. It's a very common socket type of API. You've definitely, if you've done any RE before, you may have seen socket, bind, listen, accept, connect. All those kind of calls are all very common, and they're common across not just Linux and Windows, but also other operating systems and firmwares will use a lot of these similar characteristics because they've just been time tested and they work. And people don't typically want to rewrite all of this on their own unless they have a very good reason to. But they're written in C. There's wrappers and higher level languages. Like you can do Berkeley sockets, things like this with Python. And you can also, it gives you this interface to do all this stuff in a way that is repeatable and portable across different things. So you don't have to write different drivers every time you want to go use a different computer. So a lot of times they're going to be imported from a library, unless you're on Linux and you're doing syscalls directly, which will have this stuff implemented. But you can find where these things are used based on what you know about the APIs, right? So if you're doing static reverse engineering, once you figure out which network APIs are being used, you can work backwards to figure out where the protocol is actually parsed. And actually, I wrote a tool called import sort, which is also in the resources page, which was able to take a big folder full of DLLs and executables on Windows and tell you all of the import functions and DLLs that they're calling so that you can use it to figure out quickly which of the hundreds of files you might be looking at are calling network stuff or things that you're looking for. And so once you figure out what these APIs are, the cross-references in any sort of static reverse engineering tools is typically where I start. So you can look here, this screenshot is a thing in IDA, it's IDA Pro, it's opened, and there's a call to receive, which is receiving a packet from the network. And so when you look for that, if you find that this function here, the jumps that come after are going to be part of the socket or the packet parsing functionality of the software. And so strings and error messages, if you can't figure out exactly where these things are, or if it's kind of like if you're doing anything with a language that has more complicated ways of calling functions, you can also use strings and error messages just to find things that are related to the packet processing part of the code. My favorite strings tool is Robin2. It's part of the Radari 2 suite. It's a very, very good string search. If you use anything, but that's my recommendation. And so the next part here, we'll go over this because a lot of this is going to be, again, very similar to what you do with normal RE. So if you want to look into RE and learn that whole, like the actual software RE part, there's a lot of resources you can look into that are free online about that too. So when I'm doing reverse engineering dynamic, I'll start off usually with like a tool like a netstat, or on Linux you use SS. You can use netstat too, but SS is a lot nicer, and it's built in. So you want to learn which processes are listening on what ports. Just as a baseline, it'll tell you which what the program name is, the command line arguments, things like that. If you're looking at currently running software, I'll bring up Wireshark and I'll start capturing packets too if I'm going to be doing dynamic RE. But the thing I tend to try to do is to attach to the running process with a debugger, or start a new process in the debugger to see what the flow is of packets out of this process. And so if you found functions that seem interesting in static analysis, you can then set breakpoints on those functions, and when the function gets hit, then you'll see which packet may have triggered it, and you can look for that packet inside of the program. If you send your own packets, or you just wait for it to kind of get a packet, you can follow the data all the way through the program's logic too. Another big thing too is if you set access breakpoints, which are breakpoints that are triggered when you read or write or execute from a certain area of the program image. Those are really useful for packet stuff, because if you know where the packet buffer is and you want to see which functions inside of there are manipulating data within a known packet buffer, those will typically tell you what things are accessing packets, and it can be really helpful because some software will just be really complicated in how functions are called, and so instead of wasting time on understanding all that machinery, you want to get to the real meat of it. That's typically what I try to do. So big thing here is correlating specific actions with the software, with what you see on the wire, right? So if you can do certain things, you might be able to see specific types of packets coming out of on Wireshark. So file transfers to me are really, really helpful because there'll be a lot of messages that are going to be sent, and you'll know what the file looks like on disk, especially if the file's transferred to the same computer or whatever. But you can compare those values from a file transfer to the packets of the file transfer as well. If you see here, I was reverse engineering a custom MIDI sysx extension for a keyboard to transfer files to it, and I was able to reverse engineer the whole protocol by looking at this, sending a wave file to that keyboard over MIDI and seeing the specific chunks and how they changed. Because I couldn't reverse engineer how the device was sending data, but I was able to look at the drivers and correlate the actions of transferring files, and ultimately get the structure of the packets and how it chunks data up. Another big one too is logins. If you can log in somewhere with a password or a username that you know, also very useful for you to process or to do dynamic reverse engineering. So if the whole process of doing dynamic reverse engineering is not bearing as much fruit as you would like, another aspect that another thing you can try is to do fuzzing, to do and general enumeration. And so BooFuzz for fuzzing is my favorite because it does protocol fuzzing, but in a deterministic way, which means it'll do the same set of packets as it fuzzes each time. And so you can see if things change or how it reacts to certain sequences of data. But if it's not enough for you, if you need to do more, if you want to look at a specific field, maybe you can write your own sort of thing too. I typically use Python to write my network enumeration kind of stuff for packets, because you can just do raw sockets and send data out and just increment a certain field or whatever you want to do. So writing out scripts for that kind of stuff is super useful, and having some handy, there's some in the resources page for that send frame script, things like that are really useful for doing this kind of enumeration. And also if you have like any really specific things that you want to test, I typically try to write my own stuff for it, just because a fuzzer might start doing things that I don't expect. So trying to keep things as known to you as possible is really, really good for this kind of thing. So another thing I want to also discuss too is drivers. So if you're looking at, binary or software, or whatever, and you are not really sure still where the protocol messages are, maybe they're lost somewhere, they kind of fly off into the ether somewhere, you might be dealing with something that uses a driver to actually implement the full protocol. And so drivers will interface usually with the kernel to access the hardware devices. They'll use the lower level hardware APIs to actually talk to a network interface or whatever. And it can be really difficult to figure out where the messages are constructed. Like if you look at this example here for the protocol thread, if you have an application running on, say, Linux or something, and you want to use, thread over 802.15.4, you're going to have to talk to the OpenThread API, which will talk to the core, and then to the drivers, which will build up part of the protocol message. But then to actually send the data out over the radio channel, you're going to have to send that data to the system on a chip that implements this protocol. And there's another protocol here called Spinel, which actually transfers those partially processed packets and send them over to the MAC layer here and actually send out that the full packet. So you might not even see the full packet being sent or received. You might just see fragments of it. I've seen really complicated setups where there's stuff like this, but you don't actually even send protocol data. You send some struct, and that struct then gets parsed by a network interface, and it can be really difficult to wrap your head around. So just keep all that in mind. But if you are dealing with drivers, you can typically do kernel level debugging, which there's a bunch of resources I put on the resource page too, but that will give you the full scope and be able to actually look at what the driver is doing and how it's interacting with the specific hardware. Very useful to know about. You don't always have to do this, but it's just something to keep in mind. Oh, okay. So now we'll get into hardware RE. So now, again, we're going to only be covering the basics too that are going to be relevant to protocols. There's a lot of really, really good resources for hardware hacking if you're interested in this. But this is sort of where it comes from a protocol perspective. So very similar to the software RE aspect of it. Starting off with OSINT is always usually really good. Just open source intelligence, Googling whatever you can look at on the board. FCC IDs are a really, really useful thing for people doing any sort of hardware RE and protocol RE of hardware, because typically they'll tell you about if something speaks radio, if it transmits in any way or causes any radiation, the frequency at which it does that is going to have to be logged by the FCC, at least in the US. And so those kind of things can typically tell you which frequencies are being operated at by the device, which is very useful if you are trying to, understand which protocols are in use. Another thing to look for is antennas. So if you can see here on this board, this is an ESP32. You can see that there's an antenna like on the left side of the board, and that leads to another chip. And so if you can figure out which chips are talking to which antennas, you can then figure out which protocols may be in use, because you can look at those chips and search for the markings that are on there, possibly find a data sheet. You could even potentially figure out where things are connected on the board based on what the data sheet says too. There's also things like debug interfaces, there's a lot of very standard ones here. I have a UART, JTAG, SPI, I2C, USB, SWD. Those are really common things that you'll see that you could potentially use to interface with the device. And they also have serial protocols unto themselves. So serial protocols there's a lot about them. There's a lot of ways to interact with them, and depending on what you're trying to do, you might have to reverse engineer the serial protocol to interact with the device. And so these are typically going to be the core interface of how any chip is going to talk to a main device, even your computer and the Wi-Fi chip that your computer is using, your phone, baseband, all that kind of stuff is going to be transferred somewhere over the bus of the device. And so if you can't figure out what's supported, you can use a logic analyzer or an oscilloscope to analyze which protocols are in use here. And so here's an example here of a logic analyzer. There's a lot of data here. Normally you're only looking at a few channels, but this is SPI, I2C, and other protocols all here to just show you like what it actually looks like when you are using a logic analyzer. So a lot of logic analyzer software and oscilloscopes too can decode common protocols, and then you can also put your own custom protocols into them too, depending on the software. But there's a lot of community stuff and resources for people who are reverse engineering protocols. If you want to interface with a serial protocol, it's fairly straightforward. You can use serial or USB interfaces that speak directly to the hardware. An example here is a TiGuard, which is speaks a lot of different protocols, or it provides the interface for them. And there's also USB to TTL serial dongles, which are really useful for a lot of devices. But if you don't have these kind of things, if you have like a Raspberry Pi or an Arduino or any other kind of dev board, you can use those to interface with serial protocols too, which are very standard. And I started out, I wrote a lot of stuff to interact with stuff just on an Arduino, and that was like kind of my way into a lot of this. And so here's some examples here of just attaching to UART with, this is like kind of like if you're doing a serial protocol reverse engineering, looking and actually attaching to them with either alligator clips or needle probes or whatever, you can start talking directly to the device from the chip itself and bypass everything else, which is super useful if you're trying to understand what's going on with a specific protocol. Another thing to talk about with hardware is wireless protocols, because a lot of hardware is used specifically to implement wireless protocols because they are something that gets pulled into some system and they interact with the main system on a chip. And so these can be really challenging because there's hardware requirements for speaking certain protocols. And if the protocol is implemented on a chip itself and not in software, if you don't have that specific chip, then you can't normally talk that protocol. So a lot of protocols do require custom dongles or radios, but you can also try to find those things online and maybe get your own dongles. You can also monitor raw Wi-Fi and Bluetooth frames over Wireshark too. So there are things that, as again, people don't usually reinvent the wheel. They're going to go over something that's known. A lot of stuff is done over those kind of protocols, and you can still look at them in Wireshark if you have a interface with a monitoring capability. This is an example here of a dissector that I wrote for the BLE protocol called Continuity, which is used by Apple and Apple devices with a lot of telemetry coming out of them. So if you don't have the devices that you need for speaking certain wireless protocols, you can use an SDR, which is a software-defined radio. It's just a way to visualize and decode a lot of radio protocols that are out there. There's a lot of really good ones that are very cheap. I've used an RTL SDR for many years. It's awesome. Using QRX and other things are really cool for seeing what's around you in the world in general. And you can pipe a lot of wireless protocols into Wireshark using other helper programs that demodulate the signals and actually give you the raw data, that is the binary data that's being transferred. And if you don't know what something is too, something that's really awesome that I love about the radio community is there's the Signal ID wiki, and there's a lot of places where people will show screenshots of things that are coming over their SDR and either identify them or ask for help, and people try to figure out what something is so that it contributes to the larger body of knowledge here. So now we've made it to the last of the four major ways of doing protocol RE, which is specification review. Specifications are essentially like the design document for the protocol. They are a blueprint. They tell you what they want the protocol to do. They want you tell you how they want data to be processed or managed. And sometimes they can be super thorough, and they might even have a reference implementation. But sometimes they might just leave a lot to the imagination and only consider a specific use case or set of use cases. And as a result, they can be like a blessing or a curse depending on how you look at it. So if you're reading a spec, there's a lot of things that might be really foreign or like kind of weird, just because they do give you a lot of information typically. RFCs tend to follow a similar writing style with like a table of contents, appendix, and they also have things like a document conventions sort of thing with how words are defined. There's even an RFC for the definition of words that are used in other RFCs. But vendor specs and other standards might be like really long, and they might not have data in a way that is easy for you to parse, right? Like a table or a diagram or like a data structure for a code. And so trying to enumerate the document first before you try to read it is typically like my go-to instead of trying to read it from the very first word on. So looking for things like appendixes or glossaries, things like that, you want to know how they're going to transmit this data to you the same way that you would for a protocol, right? And so the other thing too is to just try to take notes in a format that works for your needs. So if you are somebody who is I'm very visual, so I'll draw stuff out as much as I can. I use Mobius, by the way, if anybody asking about how I make my diagrams and stuff. I typically use a Mobius ANSI editor, the Blocktronics one, and also Sublime Text too. But whatever works for you is what works for you, and just try to own that process and make consistent notes that are easy for you to refer back to. Just because usually there's a lot of info. I've read specs that are 1,000-page document after 1,000-page document, and they're all linked together. Just a lot. So my big word of caution when you're actually reading specs is that they are subject to change. Even if they are very absolute in the way that they talk, there's no reason they can't change. The other thing is they can't really reference versions of themselves in the future. So it's hard to know sometimes if you're actually looking at an outdated thing, unless you do some due diligence about that as well. Sometimes you'll find a PDF that says deprecated or something on it, or outdated or something. But that's only going to be published after the fact. So just kind of look around. And another big thing too is that specs can just have mistakes, right? They ambulance there. An example, a classic one, RFC 1945 is for HTTP 1.0, and they misspelled referrer for the referrer header, but it had already been implemented and was out in the world, and browsers were starting to use it, and there was really no way to change the spelling of referrer, so it's just stuck, and we still use it even though that mistake was made in the early 90s. And as a result of all this, just knowing that humans write both specs and implementations, there's going to be these kind of things that happen. And so as a result, definitely beware of the rose-colored glasses effect, right? If you see a spec and you say, oh, this is beautiful, it tells me exactly what I need to know, you really want to look at like what is instead of what should be. Because I've wasted a lot of time, way more than just many hours, trying to fit data into a protocol spec or a header file struct or something that was given to me, and it actually didn't match what was being transmitted. And those things can be a colossal time sink if you think that it can't be me. It must be the packets that are wrong. Those are trusting what the packets are actually saying is typically my go-to, but having a lot of data sources is usually the best. So just big word of caution here. And so specs versus implementations, I've mentioned this a bunch of times, but essentially what it boils down to is that there's different implementations of a protocol can just vary greatly depending on who wrote them and why they wrote them in terms of both their features as well as their reliability. The less explicit that the actual spec is, then the more liberty that can be taken with people who are implementing it. And that can make it harder to actually compare what the spec is supposed to be with the particular implementation, and the details of a spec should really only be used as a reference. I kind of take it all with a grain of salt. And if you see something that does differ greatly, then you should examine what the difference is and why somebody would have made that change. And then the example on the right here is just two implementations of the same thing, depending on who's at the wheel. And so the last big thing about specs is just there can be holes, right? There can be undefined parts of a spec. And if something isn't defined, it's up for a programmer to figure out how to actually deal with it. And so implementations can also get things wrong due to just misunderstanding the spec and just general programming mistakes. So these are all things to consider when you're doing the kind of comparative analysis between all these things. Ambiguity definitely can lead to a lot of weirdness, as we will show. So starting off here with a protocol level bug, this one I like this one a lot because it's a very old bug. This bug existed in this specific software for longer than I've been alive, I think. So Telnet was written in 1969, right? It's one of the first RFCs that was out there. It's older than TCP/IP. It's older than a lot of things that we know about. And it was designed to interface with a teletype, right? It's a typewriter, is the old school way of entering data into gigantic mainframes. So these are written with a teletype in mind, with these certain values for sending data back and forth to people over very limited channels, right? So if you ever actually use TTY or a TTY service on a phone, you'll know about things like GA or go ahead and stuff like that. Very similar semantics are used in Telnet. And so there's this character IAC or 255 or FF, which says that the next byte that's going to be incoming is going to be a command, and to treat it as a command rather than data. And so there's a FF is sent, and then there's any one of these other things, which would be one of the special characters that is in Telnet. And so this bug has a thing where basically there's a command for you can erase a character or erase a line. And so this is sort of a thing that is just being, it doesn't tell you how to do it in the spec. It just says that you should erase the character or erase the line that comes after, right? But people have to write the software, and they can't tell how, memory, they can't predict, 50 years in the future how memory managers are going to work. And so in this case, if you're doing this on a typewriter or a teletype, there could be some physical mechanism that has to be implemented to do erasing or whatever. But in this case, if you have send an FF F7 or FF F8 without any data afterwards, if you just end the packet there, then it crashes like a significant amount of Telnet versions. And so this was a bug that was found for BGP3, and basically sending 2 bytes will crash the computer because it tries to read memory that wasn't allocated. It assumes that the data that was sent is actually there, and instead of the packet was truncated, and it could be truncated naturally, but those kind of things, if the memory wasn't allocated, then it's not going to be able to do anything and act on it. And it's just an example of how somebody might implement something incorrectly, which you definitely might see if you start taking a look at protocols. Another one that isn't specifically a protocol-related bug, but it's just a bug that I really like because it demonstrates just these very strange things that can happen with specifications, is this Chip 8 sandbox escape, which is also a part of Binary Golf Grand Prix 3 by Retroid. So Chip 8 is an emulator it can run like ROM files and stuff. This has a 12-bit address size defined by the specification. So that means that there's only 12 bits that are going to be used for the whole address space of this, which limits it to however many bytes that is. But we don't use 12-bit addresses or even things that are divisible by that in normal programming. Usually we'll have 16 bits or 8 bits for a byte or a word. And so having a non-standard size like this means that it needs to do something like a bit mask to prevent an overflow, because you're not using those top 4 bits. So you have to make sure that they're not being referenced, because all the pointers to data inside of your emulator are still going to map to pointers on your actual system. And so the spec really only knows about the virtual machine that it's describing. So it doesn't know what needs to be made, what implementations details need to be done to actually have a Chip 8 emulator. And so as a result, a lot of implementations that were doing this didn't properly apply a bit mask inside of their virtual machine. And so as a result, it allowed for arbitrary reads and writes from within the virtual machine to the actual process running Chip 8. And so if you want to read more about that, there's a link there. Really cool exploit. But this is just a common example of there's going to be stuff like this that exists in the world still that has to be backwards compatible, and it has assumptions that are based on very old styles of doing computer stuff. Those are the kind of things you definitely want to take a look at if you are trying to do vulnerability hunting specifically. And then one more thing I wanted to discuss too is parser and dissector challenges that can happen as a result of a specification. So this one isn't particularly a protocol-related bug, but it's going to be very similar things. So just an example here of a type of thing that I found with ELF files, which is when you run an ELF file, you run any kind of binary, but specifically ELF, the operating system is typically trying to set up the program as fast as possible and execute it. It doesn't want to waste a lot of time on processing because, it just slows down the total start time of a specific process. And so the operating systems don't typically check all the fields inside of an ELF. One of the ELF fields is called EI data, and it's the endianness field that tells you whether something's big or little endian. But all the operating system really cares about is whether or not the machine type, which is the actual architecture, matches what is it knows it can run. And so usually what the kernel will do is just it'll map the file after it checks to see whether or not it's for the architecture that the kernel currently is, and then it just tries to run it after it does all its basic mapping it needs to do. But it doesn't really care, because if it doesn't work, then it just has a segmentation fault or an illegal instruction. It doesn't really care whether or not it's the endianness. It just tries to do it, and if it works, it works. But that doesn't really, it's not really that good for a dissector or parser perspective, because all these other metadata fields that you want to know are still present, and they're still useful for you to understand the binary. But because there are discrepancies between what is actually needed to run the file versus what data is stored in the file, that can lead to issues here. So in this example here, this file analysis tools can be tricked with ELF by changing the endianness to a value that doesn't work with the architecture you're using. So if you have a incompatible parameter, like say big endian x86, then the binary analysis tool might try to process all the addresses that are inside of the file as big endian instead of little endian. And there's some cases where you can actually allocate too much memory and DOS the program, or it can just mess up how the analysis is. And so this is from my example in temp out of pretty much every tool, by just changing one bit inside of an ELF header, does not know what the file is anymore. And it also works on VirusTotal too. VirusTotal was changing one bit from like a known piece of malware to changing that one bit in the header would result in all the signatures not working anymore. And so this is also a thing that can happen with dissectors as well. If you look at the issues in TCP dump or Wireshark, you'll see some examples of that. So now this last little part here is just about how to document what you found. And so there's a few different things that I typically do, but one of the things that has helped me the most for documenting any kind of protocol, even if I don't need it, is to write a Wireshark dissector. And they're super handy for tracking protocol messages in general and finding data, because if you can start slicing stuff into fields, then you'll be able to pivot on that data, because it's extra data that you're able to have as a characteristic of a specific message or whatever. And so you can use dissectors also to add filtering, to filter out whatever you want from the traffic that you're analyzing. And they can also be really helpful for just tracking your findings in general, right? So I usually write them in Lua just because they're easier to write. But you can also write them in C, but it definitely is harder to do the kind of rapid prototyping if you're doing research in C. So I try to stick with Lua for writing a dissector. It's not my favorite language in the world, but I will write it for this purpose. Also, fun fact too, I think I put a TikTok in the resources page, but you can run Lua scripts from Wireshark from the command line. It's kind of like a lull bin. So if you ever need that, you should know. Oh yeah, and also this was a custom dissector that I wrote for a internal protocol in Postgres, which is just an example of what you can do to understand a protocol better. But another thing you can write too is just your own parser or your own implementation. And so I'll typically write stuff in Python, just even if I need to analyze a small subset of messages, but it can be helpful for doing like quick little analysis work, as well as constructing messages to send to say do your own testing or enumeration. And here's an example here of this custom client that I wrote for MIDI after I RE'd a bunch of stuff. This is to grab data from a synth because there was no driver that existed for Linux at the time, which now there is, which kind of rendered this all useless, but it was still good. But you don't have to go, all out with it. You can write partial implementations if you need to. I mean, you can do a full thing if you really want to, but a lot of the time it's just for being able to transfer information to others or to be able to have a reference model for yourself, which is really cool. Other type of documentation that you can do as well. I mean, you don't have to always implement the whole thing. But if you have, say, like a struct or a header file that you wrote that can represent the data structures inside of the packet, those are super useful. Same with writing tables. I like doing tables like this, and you can do Markdown, and this is the Wikipedia for TCP segment header. But doing tables, any way that you can do to represent the structure visually is really good. There's also stuff like KaiTai, which is a template sort of language for describing structures of binaries, which I really like. And same with 010 structs, which are very similar to C, but you can apply them to a hex editor. I think IMHEX also supports those too, I'm pretty sure. And then I also wrote the XX file format to do this sort of like pretty documentation, because I used to do, when I did reverse engineering to share with other people, I'd have to show them very quick work of this kind of stuff. So being able to document what the fields meant in a way that was repeatable, that people could then construct their own files out of. That's kind of what the main point of it was. The last thing is ASCII diagrams, which I like to do as well, just coloring in stuff and pointing to them. But whatever works for you and whatever works for your team or whoever you're working with, you should definitely try to agree on that first of what your documentation style is going to be, so that you'll at least know what to ship, so that everybody's kind of working on the same page. And the last little bit here is the healthy research mindset, which is something that I always try to tell everybody who is doing this kind of work. So this is just my abyss gazer tips. If you're staring, deep in the rabbit hole here, things you got to know. So definitely it can be a supreme rabbit hole to look at protocols and do reverse engineering. It definitely can feel like you're playing Tetris for a long time. Very similar if you're looking at just hex data. It's a whole different mindset from most other things you have to do. So make sure that you take breaks and take care of your IRL needs as much as you can. Set timers. Those are big things for me. I set timers for myself all the time. Have things that also exercise other parts of your brain in your life, because if you do not allow yourself to unattach from the research mindset, it can cloud how you actually view the research problem in itself. Like sometimes you can just go for a walk and get some inspiration or just reset yourself. It's really, really handy. Also, if you can, depending on, you might not be able to, but if you can, talk to other people about your project when you can, right? If you're going to be venting about something or need a place to post some memes or whatever, or just somebody to rubber ducky, bounce ideas off of, try to establish those kinds of people. If you're doing like NDA'd work or contract stuff and you can't really share it, work with your team as much as you can, and maybe even have like a water cooler, whatever you can do to kind of like get this energy out, because you take in so much, right? And you have to do something with that energy. So, yeah, very useful. And also give yourself enough time to document your findings and actually clean up your notes and do goal setting, because the amount of like little scratch pad, note files and untitled, 20 different untitled Sublime text tabs, that can get really overwhelming. And if you take a break without doing the sort of documentation that you need to do, or if you take a long period of time where you can't work on it, have to switch, it can be very difficult to parse all of that. So if you can make yourself your own little design document about what you're working on and give yourself time to do that, very, very useful. But ultimately, you figure out what works best for your style of research. You're only human. You're not going to be able to do this 24/7. So figure out what works for you and be kind to yourself and the people who you work with. And yeah, thanks for everybody for listening in on the stream here. There's a lot of crazy protocols all over the place. Don't be afraid of them. Look at them. Share as much as you can. There's a lot of really cool stuff that you can do. There's contributor pages for Wireshark. If you make it a sector, you can contribute them to Wireshark, and you can even contribute to the core sectors on there as well. There's a lot of stuff that is just useful for people who are doing all sorts of RE. So, even if you're doing it just for fun, it's still valid. Go out and do it. There's a big page that I wrote here for references and further reading. But if you need, if you want to add to them, you totally can too. My website is n0.lol. So if you ever want to look at any of the other work that I've done, check it out. And thanks to everybody and Prelude for this stream. Bye.